Okay, so now we discuss about the strong acid and strong base. So strong acid is the species that is completely dissociated in aqueous solution to produce a high concentration of H3O plus. Okay, so strong acid will have alpha is equal to 1 or 100% dissociated. For example, we have hydrochloric acid, which is a strong acid, react with in water to produce H3O plus with a Cl minus. Okay. Next, we also have HNO3 uh, to produce H3O plus and NO3 minus. Okay, note that if we have 0.5 molar of nitric acid, so it means that we will produce 0.5 molar of H3O plus and 0.5 molar NO3 minus. So that is what we meant by 100% dissociated. Okay, there is no more HNO3 as the reactant when it is introduced in the reaction with water. Okay, meanwhile, base is the species that is completely dissociated. Okay, strong base, completely dissociated to produce the high concentration of OH minus. Okay, OH minus, and as same as a strong acid, alpha is equal to 1. Okay, alpha is equal to 1 or 100% dissociated. Okay, so the example of strong base is sodium hydroxide. Okay, note that, okay, for strong acid, we can write the equation HCl aqueous plus H2O liquid to produce H3O plus and Cl minus. So this one is correct. Or we can write the equation as HCl aqueous dissociate to H plus uh, and Cl minus. Okay, this is also correct. Okay, for acid, strong acid only. Okay, for strong base, we cannot write NaOH with water. Okay, if you write water with the reaction of NaOH, you will have difficulties to what we say balance. Okay, the equation. So we just dissociate. Okay, separate OH minus from NaOH. Then we get Na plus and OH minus. So that is the way how we write the equation for strong acid and also strong base. Okay, if we have a strong acid, strong base, we also have the weak acid and weak base. So weak acid is the species that is partially dissociated in aqueous solution to produce low concentration of H3O plus. Okay, so we have the percentage dissociation, which is less than 100%, or alpha is very small than 1. So note that the arrow that we use here is reversible arrow. So reversible arrow is to show the reaction is for weak acid or the reaction for weak base. Okay, so the reaction of acetic acid is the species that donates proton. So we remove the proton H plus here, and we will get CH3COO minus and H3O plus. Okay, so this is the equation. Okay, so either you want to write the reaction with water or without water, it is accepted. Okay, for for weak acid. Okay, for weak acid. Okay, so weak acid. For partially dissociated acid, we have the value of Ka. Okay, value of Ka. Okay, so Ka can be the expression of Ka can be written as concentration of CH3 COO minus, okay, times with concentration of H3O plus. Okay, so this is the aqueous, okay, aqueous over concentration, okay, of the reactant of CH3COOH, okay, CH3COOH. So here, okay, take note that we exclude, okay, the concentration of H2O since it is in liquid form. Okay, the phase is liquid, so as it is excluded from expression of Ka. So Ka is what we say is the identity of the weak acid. If the question asks you if you have a question and it gives you the value of Ka, so it means that we are dealing with weak acid. Okay, so Ka is the acid dissociation constant for acid. A is for acid. Okay, acid dissociation constant. Okay, Ka, and we also have Kb. Okay, Kb is the base, okay, dissociation constant Kb. So the expression is the same, okay, is the same as Ka, which is here we have OH minus and also NH4 plus, okay, over with concentration of NH3. Okay, so since the value of Ka and Kb, you can see that the value is somehow exponential -5 or exponent -7, -10. So it shows that the value or the dissociation of the weak acid or weak base is very small compared to the initial concentration. So later on, I will show how we determine or how we calculate, okay, the question, okay, that is related to Ka and also Kb and also alpha. Okay, so don't worry about that. Okay, so next we have the pH measurement. Okay, so the pH measurement, we have the range from 0 to 14. For 0 until 6, okay, 6. So 7 is what we call as a neutral, neutral. And 0 to 6 is the acidic, okay, acidic, pH acidic. And from 8 to 14 is the pH of alkaline. So what should we know about the pH of 0 to 6 or the acidic pH? So acidic pH, it shows that concentration, okay, for acidic solution, when the pH is less than 7, we have the concentration of H3O plus is greater than concentration of OH minus, okay. So pH is the measurement of the concentration of H3O plus, okay. So pH, H here is the measurement of the acidity, okay, acidity of the species or the solution. We measure it with pH, okay, pH. So for acidic solution, we have the concentration of H3O plus is greater than concentration of OH minus. Okay, for solution with a pH greater than 7, okay, the concentration of OH minus is greater than concentration of OH minus. So if we have pH, we also have POH. So so you can read by yourself. POH is a measure of the concentration of hydroxide ion in the solution. Okay, so jadi if pH, okay, the value of pH is calculated by the formula of negative logarithm concentration of H plus pH. Okay, POH is negative logarithm of concentration of OH minus. Okay, note that okay, pH plus POH is equal to 14. Okay, equal to 14. So when pH and POH is equal to 14, okay, remember this. It will show the what we say the concentration of H plus and concentration OH minus also from the value of pH. Okay, so you need to do a lot of practice to familiarize with the measurement of pH and POH and also the formula of pH plus POH equals to 14. Okay, so it is all about the practice. Okay, so let us see the first equation that the first question to calculate the pH of 0.20 molar of sulfuric acid. Okay, so 0.2 molar of sulfuric acid. So how do we solve this type of question? Okay, so write the equation. Okay, H2SO4 aqueous plus H2O liquid dissociate. So this is strong acid, strong acid, because the question didn't give you any value of Ka or Kb. So sulfuric acid, we know that it is acid, so strong acid. Okay, strong acid completely dissociates to H plus ion and sulfate ion. Okay, so this one is H2, this is 2H plus, aqueous plus SO4 2 minus, okay, also in aqueous. So if you have the initial concentration of H2SO4 is 0.2 molar, okay, 0.2 molar. So the change in concentration of sulfuric acid will be minus 0.2. Okay, strong acid will dissociate completely. Okay, so minus 0.2, and the product will be 2H plus. Okay, 2H plus. So 0.2 is somehow minus X. Minus X. This one will be plus 2X. So plus 2X, we know that our X is 0.2 here. Wait, so I think we need to do another method before you grab the concept. So I will show you one by one. So this one is minus X. Okay, this one is plus 2X. Okay, 2X, and sulfate also plus X. So concentration, final concentration, it will be 0.2 minus X, okay, and this one is 2x and x. Okay, so we know that strong acid, okay, strong acid, the value will be 0. Okay, so completely dissociate. So 0.2 minus x is equal to 0 and x is equal to 0.2. So when x is equal to 0.2, substitute all the value of 0.2 here. So 2 times 0.2, and this one is 0.2 only. So this one will be 0.4 and this one is 0.2 only lah. Okay, so here from 0.4 that we get, we can calculate pH. Okay, pH of 0.2 molar sulfuric acid. So the formula of pH is equal to negative logarithm of concentration of H plus. Okay, so now the value of H plus is 0.4 molar. Okay, 0.4 molar. So you substitute negative log 0.4. Okay, then you will get the answer. Okay, for the first question 1A. Alright. Okay, we get the answer. So what I want to show here, what is the coefficient. Okay, you need to check lah whether the dissociation will produce 1 mole of H plus or 3 mole or 2 mole of H plus. So it depends on the molecular formula or the formula of the acid, okay, to determine the concentration of H plus. Alright. Okay, so this is for sulfuric acid. So you can try about 4 what we say base and so on. Okay, so for question number 1. Okay, for question G. Okay, so what I have here for question G, that we use the value of Ka. So how we solve the pH, okay, of the for 1.5 molar of benzoic acid. So benzoic acid given Ka. Okay. Okay, so what you should do, the first thing is you need to write the equation. C6H5COOH plus water to produce C6H5COO minus. So acid is the species that donates proton. Means that you separate H plus here and it will become C6H5COO minus, and H plus is donated to H2O plus with H3O plus aqueous. So this one will be is the aqueous, and this one is the liquid. Okay, so what we can do here is we write the ice table. Okay, so ice table. So the dissociation table for 1.5 molar of benzoic acid. So starting we have the initial concentration 1.5. Okay, so we write here 1.5. This one is, we can put dash. This one is 0, 0. Okay. So for weak acid or weak base, we need to come out with the table. Okay, dissociation table. Then we have the change in concentration will be minus X. This one, since 1 mole, so plus X and plus X. Okay, so Ka, since Ka, acid dissociation constant. So this is the value of concentration at equilibrium, this will be 1.5 minus x, x, and also x. Okay, we solve for x. Okay, how we want to solve x? Okay, you write the expression for Ka. Ka is a concentration of C6H5 COO minus. Okay, C6H5 COO minus times concentration of H3O plus over, okay, so we take here the aqueous 1.5 minus x. Okay, 1.5 minus x. So, the value is 6.3 times 10 to power negative 5. Okay, 6.3 times 10 to power negative 5. So, since the value is small, okay, it's very small. So, the value of Ka, okay, so we can write Ka is smaller than 1. It's very, very small than 1. Therefore, you punya value, therefore the value of 1.5 minus x will be 1.5. Okay, so means that if the value of Ka is very small, you will get the value when you solve for the value of x, you will get the value of x is also very small. So we just assume that 1.5 minus x is equal to 1.5. Okay, then you substitute 6.3 from here. You get 6.3 times 10 to the power negative 5 is equal to x. So this one is x squared over 0.15. Okay, so minus x is we neglect okay, the negative x here. Okay, so you solve for the value of x. Okay, so the value of x is similar, okay, as the concentration of H3O plus. So means pH is equal to negative log concentration of H3O plus or negative log x. Okay, here is a negative log x and you solve for the value of pH. Okay, so I think that's all for the dissociation reaction of strong acid, strong base, and weak acid, and also weak base. Okay, so although I've only shown you the reaction of strong acid and weak acid, but it is similar to the reaction of strong base and weak base, but the value that we calculate is the value of POH first and then we convert it to pH. Okay, so you can try it by your own and we will discuss more about POH in the next lesson. Okay, so I think that's all for today. Thank you for listening.